Who likes video games? Awesome, all right. Well, you're in the right place. Next question though. I see people put their hands down, that's fine. Who uses their web browser to play their favorite games? Oh, there's a couple, all right. I'm gonna talk to you afterwards and learn a bit more. But for everyone else who didn't put your hands up, prepare for some hot takes. Before we get started though, I just want to take a moment to thank our sponsors and community partners. Their generous support made today possible, and I'm really grateful for this opportunity to come up here and speak to you all today. Today we're going to take a journey through the history of web gaming. We're going to look at the early days of browser plugins and Java applets, and then explore some of the challenges that were faced by pioneering technologies like WebGL. Then we'll explore the advancements of WebAssembly, ECS, and WebGPU that are revolutionizing web gaming today. Each one represents a significant leap towards bringing web gaming closer to native level performance right from your browser. So let's start with a look back at web gaming's golden age. So in the late 1990s and the early 2000s, web gaming was led by technologies like Flash and Java applets. These browser plugins let developers create rich interactive content that ran directly in the browser. And that allowed games to be more accessible than ever before. They sparked a new era of online entertainment, and they laid the groundwork for the vast gaming communities that we have today. For Java applets, we had iconic games like RuneScape launching in 2001, and the early versions of Minecraft that were originally playable via Java applets. And then on the Flash side, there were hugely popular titles like Club Penguin in 2005 and Bloons Tower Defense in 2007. And these games and many others were pioneers at the time and really pushed the limits of what was possible on the web. So what happened? This guy. In 2010, Steve Jobs published an open letter called Thoughts on Flash, where he controversially claimed that Flash is no longer necessary to watch video or consume any kind of web content. He also cited concerns about security, performance, and battery life. But in retrospect, I think we can probably agree that plugins were holding the web back. But that decision to not support Flash on iOS devices effectively signaled the end of that Flash era, and it pushed the industry towards open web standards. So developers were now faced with the challenge and the opportunity to find new ways to deliver rich web content without relying on plugins. So the web community turned to technologies like HTML5, and then about a year later, WebGL was introduced. WebGL brought hardware-accelerated 3D graphics to the browser without relying on plugins, but it faced significant challenges. It was based on OpenGL ES 2.0, which was designed for embedded systems, and so it lacked some of the advanced features that were found in desktop graphics APIs. And developers also just struggled with less mature tooling and a really steep learning curve because of a lack of tooling. This just kind of hindered widespread adoption for complex game development for many years. Now, this isn't to criticize WebGL, but it was facing a steep uphill battle, and it continued to do so for many years. Then we get to 2017 and the introduction of WebAssembly, or WASM. So that was a real game changer for web development. Just for those who aren't aware, WebAssembly is a low-level binary instruction format that that acts as a compilation target, allowing you to run code that's written in C, C++, and Rust in the browser at near native speeds. So it's designed to work alongside JavaScript to complement it, not as a replacement. And it allows developers to leverage their existing web APIs and frameworks and then boost performance where it's really needed. So how does it do that? Well, it's designed for high performance with this compact binary format. It loads and runs at speeds that are comparable to native execution, which is just critical for games that kind of rely on intensive computation and real-time processing. It offers more predictable performance than JavaScript because it doesn't rely on the just-in-time compilation that JavaScript does. And it also uses a linear memory model that allows developers to manage their memory more directly and efficiently if they know what they're doing. And so unlike JavaScript's automatic garbage collection, WebAssembly lets you manually allocate and deallocate memory. So you can reduce the overhead, and critically you can reduce the garbage collection pauses, giving you just a more smooth gameplay and more responsive feel. It also leverages instructions like SIMD instructions, which enable parallel processing of data on the hardware level. And that's really useful for like heavy mathematical operations like graphics rendering and physics calculations. And lastly, it also just allows developers to bring their existing code bases to the web. Like for example, I'm currently working on a game that uses a physics engine that was originally written in JavaScript. And we were able to reduce the CPU utilization of our physics calculations by about tenfold by switching to the Rapier physics engine, which is written in Rust. And we're able to bring that performance benefit to players right in their browser. So as a direct comparison, I want to reference a project called WasmBoy. This is built to bring playable Game Boy emulation to like budget mobile phones and Chromebooks. I encourage anyone to check it out. It's really interesting. So it uses, the QR code is there if you're interested in following it. It uses a language called AssemblyScript. If you're not familiar with it, AssemblyScript is a subset of TypeScript, but it directly targets the WebAssembly runtime. So they have this code alongside ordinary TypeScript, allowing that same project to compile both WebAssembly and JavaScript modules. So this lets WebAssembly kind of handle the heavy processing like graphics and sound processing, and it just lets JavaScript handle those simpler interface tasks and just the web integrations. So interestingly, and they do this in the benchmark here, so the AssemblyScript code itself can actually also just be compiled straight to JavaScript by just mocking out some of these WebAssembly APIs and then just running it through the TypeScript compiler. So because of that, they were able to do this benchmarking using nearly identical source code, comparing WebAssembly to JavaScript. So in this study that I've kind of got here, that I'm showing the data for here, they used the Back to Color ROM. This is like a kind of demo app for the Game Boy, and they ran it on a 2015 MacBook Pro. And you can see the results here. So basically on Chrome, WebAssembly ran about 70% faster, but on Firefox, you can see the huge difference there. WebAssembly was about 12 times faster than JavaScript on Firefox. And like this is not necessarily just to kind of criticize Firefox, right? But it highlights not only the speed advantage, but just the general consistency between devices because, again, WebAssembly gives you that more predictable performance and you don't have those JIT performance cliffs that are just unavoidable when you're using JavaScript. However, during this period, native game development hadn't been sitting idle. The growing complexity of games had kind of led to your traditional object-oriented programming approaches becoming a bit unwieldy for like large-scale projects. And you had Scott Bylas introducing component-based architectures at GDC, like during the 2000s, and then those ideas evolved through the 2010s into the entity component system architecture that's popular in game development today. Did anyone check out James Morgan's talk just now on creating a game engine? Cool, it's a great talk, James, if you're in the audience. But just for those who missed it or who are otherwise unaware, ECS is a software architecture that essentially just emphasizes composition over inheritance. So it just allows you to make more flexible and scalable game systems. At a high level, an entity is just a unique identifier. It could represent a player, a projectile, enemies, walls, anything really. And a component holds the data that's associated with that entity, like its position, its velocity, or its health. And then the systems contain the logic that will kind of process the component data and update it accordingly. So you might have like a physics system that will read the velocity component data and then update position component data accordingly. So a significant strength of ECS is in that flexibility and the reusability. Like for example, you can take any entity in your game and turn it into a damaging projectile just by like attaching a bullet component to it or something. And then that tells some downstream system to deduct the health from any entity that collides with it, right? So you get a lot of flexibility that way, but ECS also lets you overcome another significant obstacle to performance if these components are well designed. Is anyone familiar with the memory wall? Possibly, you might not know it by name, but basically it refers to a performance bottleneck that's caused by this growing gap between processor speed and memory speed. So you can see it started becoming a problem in the 80s, and it's just become exponentially worse since then, because any time the processor has to transfer data to and from memory, it has to wait for that operation to complete. So it can spend a ton of time, waste a ton of time just waiting for those operations. So it's basically like having a calculator here, right? And you need to perform some calculation, but in order to get the parameters for that calculation, you need to drive down to Fremantle, look up the data in a filing cabinet, and then kind of bring that back and then put it into your calculator. Like it's crazy. I mean, who would write software like that? I mean, we all do. It's a normal part of programming. Like your program is going to use memory. But you know, if you design things well, there is a way to mitigate that overhead. I watched a presentation from Daniel Sagenschneider at DDD Perth in 2021 about building a high-performance web server. And he said something I thought was really insightful. So he mentioned that software doesn't make a system run faster, right? Because the hardware is ultimately what sets the limit on speed. But what you can do with software is make it run more efficiently by aligning it with the design of that hardware. So CPUs have caches, right? Like L1, L2, and L3 cache. And these are really fast. Like reading from the L1 cache is about 60 times faster than reading from main memory. So they're really fast, but they're also very small. So to optimize the efficiency of your software, you want to design things so the processor can use these caches as much as possible. So basically, instead of like driving down to Frio and back every time you want to do a calculation, you want to design your data so that you can go down there, but then bring a whole drawer back from the filing cabinet and then just sit that in a cache next to your calculator and then just kind of work your way through the data in there doing the calculations one after the other. So by storing this component data contiguously in memory, we can maximize the cache efficiency and just reduce these cache misses, which is one of the core principles of data-oriented software design. So for gaming, it means that systems can process more entities per frame and just give you smoother animations and just more responsive gameplay. So by combining ECS with WebAssembly, you see there's a very strong synergy for web game development. You've got web gaming's near-native processing speed and this direct memory access, complementing ECS's scalable data-oriented design. So together, they let us build complex high-performance games that can just run straight from your browser. Now, building on top of those, the keystone technology here is WebGPU. Now, this only arrived last year in Chrome, becoming available by default in Chrome last year, and now in Edge as well, being Chromium-based. But it's still experimental in Firefox and Safari as well, behind kind of like feature flags and so on. So this is still very much a bleeding-edge technology. But WebGPU provides a modern low-level access to the GPU. So similar to these contemporary desktop APIs, like Vulkan, Metal, and Direct3D 12. It gives you more direct control over the graphics pipeline than WebGL, and it gives you access to advanced GPU features that just can push web graphics performance to the next level. So how does it do that? Well, the most prominent feature that it provides is access to compute shaders. So compute shaders allow you just to do general purpose compute on the GPU, kind of enabling developers to do tasks like kind of cloth and hair physics simulations and like particle systems, just purely presentational compute on the GPU, which is just much more optimized for parallel processing. You can actually do this in WebGL, but it involves a hacky workaround of getting your data, encoding it into a texture, and then uploading that texture to the GPU, decoding it in your shaders, doing the compute, marshalling and unmarshalling and so on. So it can be done. Obviously, it's much easier in WebGL. It's like a first-party function. WebGPU also gives more explicit resource management. So developers have more control over memory allocation and resource binding, just giving them more optimized use of GPU resources and really being able to have full control there. And also, it just exposes these modern graphics features, like bind groups and pipeline state objects. The details of a lot of these features are kind of beyond the scope of this talk, but the overall takeaway is that it just gives, it results in developers having access to creating more efficient rendering pipelines and just overall a better developer experience that's kind of closer to what you would get if you were building a game for desktop. But just as by way of like raw performance comparison, there was an experiment earlier this year, again, you can follow through the QR code if you're interested, that directly compared WebGPU and WebGL for rendering particle simulations and rotating cubes. Again, I won't go into too much detail, like it's a fairly simple experiment, but the key result was that WebGPU consistently outperformed WebGL across all the tests, achieving a higher frame rate, and that gap increased as the load increased. So we kind of got up to like nearly 28% faster, higher frame rate at rendering like 2 million particles. So when we integrate WebGPU with WebAssembly and ECS, we get literally unprecedented capabilities. We've got ECS ensuring optimal data organization and processing. We've got WebAssembly handling compute-intensive logic very efficiently with that optimized data transfer. And again, we have WebGPU now providing GPU computations and access to these advanced graphic features. again with that optimized data transfer. So the combination of these three really lets us fully leverage the CPU and the GPU right from the browser. Let me just go back. So before we move on, let's just have a little check and see what this actually looks like. So this is a demo. How's the color? It's okay. Hopefully you can make that out. This is a demo of a game called Space Lancers, which is quite hard to control from a trackpad, but you can see this is I'm going to crash. Okay, I'm just going to stop playing. You can see that, that this is a very high fidelity, kind of full 3D gaming experience, but this is just running in ordinary Chrome. Kind of got the toolbar there. You know, we can crack open the dev tools if we want. And now I'm going to do something that you never do in a live demo, and I'm going to reload the page. Okay, so far we're looking good. Okay, I think we got there. So that's it, fully reloading. Now, full disclosure, this game was cached in the browser, right? But even so, I don't really have any games at home on my desktop PC that can load that fast. And definitely none that are accessible just by sharing a link. So we've seen where we came from, and we've seen where we are now. So what's next? Well, from a technical perspective, the download footprint is always going to be a problem, right? So developers will need to kind of be much more deliberate about designing their code in creating modular code to minimize the amount that needs to be downloaded up front and get you into the game faster. Now, you already kind of see some of this in kind of games doing background streaming, but obviously for web gaming, it's much more important because people on the web they expect that instant feedback, right? So, and you also need to use, obviously, very robust browser caching rules to maximize the use of the cache. But even so, browser caches are volatile, right? So more stable caching solutions would definitely be a big help. Honestly, though, like the other major challenge for web gaming, and developers don't really like admitting this, is just marketing and discoverability. And this is something that like app stores and launchers like Steam handle really well. But there's no real central web gaming hub kind of that is commonly accepted. I mean, there is growing popularity on sites like itch.io and Poki.com, Arcadium, and we've got products like the Ray browser, which is just specifically built for web gaming. So overall, web gaming is a rapidly evolving space, and it enables developers to create games that are instantly accessible, highly performant, and visually stunning. And I can't wait to see what we can build together. Now, I've got a few QR codes up here. I recommend, though, don't open them until you get home, probably, because it's about a 400 meg download. Not sure what the Wi-Fi is going to do. Space Lancers you've seen, and Lyra is the starter app to showcase Unreal Engine, but it's available here just to play in your browser as an arena shooter. Now, I'm not sure if we have any time for questions. If we do, we will go through them. Otherwise, I'll see you all on the web. Thanks.
Thank you, Leigh. All right, we've got time for one question. Yes.
Thanks. Very useful information. So I can see, because currently there's a lot of AAA games sort of running in a live server mode where they're constantly updating content. So in the future, I can potentially, there's a potential that those games can be served on the web browser. But let's say from here to there, where do you see there's still gaps that we need to fill in to sort of achieve this purpose so that people can just open the browser, probably wait a little bit, and then they can start playing without a lot of restriction of downloading large size contents and all the other obstacles?
Sure, yeah, well, I touched on it a bit during the kind of the what's next section, right? Because your question is kind of like, you know, the holy grail, really, of where we do go next from here. Because, I mean, ideally, as I was kind of saying, that the technology is there, right? You can create AAA games in a browser, but it's a bit of a chicken and egg situation. So I think really to get to that next level, we sort of need, I suppose, to solve the marketing, that discoverability problem, and this initial download experience. But ultimately, you're definitely right about the live service model being perfect for the web, and that's a huge advantage that you have because you can update your game, you can patch your game, and as long as you've got clever browser, clever caching going on, people are just downloading just the bits that are changed. So you can really, it makes the developer experience obviously much better. I mean, I'm working in instant games at the moment, and just not having to go through this full release cycle every time you want to patch the game is huge. So there's a huge amount of potential here. But I think, and we are seeing growth in the space, but we just kind of need to continue sort of supporting it, I think, as we go forward.
All right. Thank you so much, Leigh. Give one more round of applause.